Hey all, welcome to this lecture of Artificial Neural Network. In this lecture, we will be discussing about the learning process of an artificial neural network. Before going to that, what is learning in the sense of an artificial neural network? The learning process in the case of neural networks constitutes of the following sequence of events. In the first sequence, the neural network or NN is simulated by an environment. Then, the NN undergoes changes due to this simulation. And finally, the neural networks respond in a new way to the environment due to this change. So, the learning process is as simple as this. If you look at this, you can see the similarity between these sequence and how our brain learns, right? Now, coming to the formal definition of learning. Learning is a process through which the free parameters of a neural network are adapted through a continuing process of stimulation by the environment in which the network is embedded. And the type of learning is determined by the manner in which the parameter changes take place. So, based on this, we can define 5 learning mechanisms or learning rules or learning algorithms. Okay, and they are error correction learning, memory based learning, Hebbian learning, competitive learning, and Boltzmann learning. So, in this lecture, we will be concentrating mainly on error correction learning and memory based learning. Okay, now without wasting time, we'll go to the error correction learning. Suppose we provide a stimulus vector x of n as the input to the network in which neuron k is embedded. Okay, then the actual output response to this x of n by the neuron k will be yk of n, and the desired response of neuron k to the input x of n be dk of n. So we can see that there is a difference between the desired response dk of n and the actual response yk of n at time n, and we define this quantity dk of n minus yk of n as error signal ek of n. Okay, so what is error signal? Error signal is the difference between desired response dk of n and actual response yk of n. Now, the ultimate purpose of error correction learning is to minimize some cost function based on ek of n. Now, there are a lot of cost functions used in this learning based on the environment, inputs, etc. And one of the most common type of cost function is the mean square error criterion, which is defined as E of n equal to half sigma ek square n. And as I already said, in each iteration, we try to bring the value of E of n to the minimum possible value. Okay, so suppose E of n plus 1 is less than E of n. Then we will update the synaptic weights using delta rule, which is given as eta ek of n into xj of n. This is also called Woodrow-Hoffmann rule. Okay, and the name for this is delta rule, also called error correction learning rule. Okay, where this eta is a positive constant that determines the rate of learning. In other words, we can say that adjustment made to the synaptic weight is proportional to the error signal and the input to the synapse in consideration. Okay, and with this we will update the weight of the synapse such that wkj of n plus 1 is equal to wkj of n plus delta wkj of n. Okay, now with what we have learned till now, we will try to draw the signal flow graph of error correction learning. Okay, so as you all know, this is the signal flow graph for a model of a neuron. Now, for the simplicity, I will consider only one of the inputs, xj of n. Okay, and I will delete all other inputs. Also, we know that for a signal flow graph, for the first case, let this input be x, input not be x, the synaptic weight be w, and the output be y. In the second case, let the input not be w, the synaptic weight be x, and the output be y. In both cases, we know that the output would be xw, right? Using the same principle, I exchange the synaptic weight and input position here. So the input node will contain wkj of n and the synaptic weight will be xj of n. Okay. Now the first thing we have to generate is the error signal ek of n, which is dk of n minus yk of n, right? For that, I will update the signal flow graph in such a way such that I will take another node which is fed from the output yk of n and is multiplied by minus 1. Now I will take another source node with the dk of n as input and produce its output to this node. So what will be the output over here? The output over here will be ek of n, right? See, from this part we will get minus yk of n, and from this part we will get plus dk of n, which is nothing but ek of n, right? Now the second part of the equation is wkj n plus 1 equal to wkj n plus delta wkj of n, right? And we know that delta wkj of n is nothing but eta ek of n into xj of n, right? So in order to get wkj of n, I will take this ek of n and multiply it with eta xj of n. Is that okay? Right? Now I'll fed this input to here. Okay. Thus we have completed half part of this equation. That is, we have provided delta wkj. Now we have to provide wkj of n to this node, right? For that, I will take the wkj of n from here and I will fed this into here. Is that okay? Now the output of this node will be summation of this signal and this signal. And what is this signal? This signal is nothing but eta xj of n into ek of n, and this signal is nothing but wkj of n, right? Now this wkj of n plus 1 should be the weight in the next iteration. In other words, we can say that this wkj n plus 1 should be fed to this node only in the next iteration. For that, we will introduce a delay element over here. What does a delay element do? For example, x of n into delay element gives us x of n minus k. Okay. So using this logic, the wkj of n plus 1 will be used as the new weight in the next iteration. So to summarize, this is the signal flow graph of error correction learning. Now another thing to discuss is the shortcoming or drawback of error correction learning. See, we know the first function e of n equal to half into sigma ek of n, right? Now the objective of the error correction learning is to minimize this function, right? So if we draw a graph between e of n and synaptic weight w kj of n, where j is held constant. Okay. Now suppose we started the iteration from 0, n equal to 0, and with each iteration the graph went on like this, like this, like this, like this. Okay. Now we take the lowermost point of this function. Okay. Let this be n1. Now if we take the next iteration, that is n2, we can see that e of n2 greater than e of n1. So the learning process assumes that we have reached the lowest point at n1 and terminate the learning process. But if we extend the graph, we may get another point which is even lower. Let this be n3. And the error function e of n3 will be less than e of n2. So actually the algorithm should have terminated only at this point. But due to this local minima over here, the algorithm terminated over this point. This is a shortcoming. So in a multidimensional space with nonlinear inputs, the algorithm may get trapped at the local minima and may never reach the global minima. Okay. Thus we have concluded the error correction learning rule for artificial neural networks. Now we'll move on to the next learning rule, that is memory based learning. Memory based learning. In memory based learning, we mimic the way the brain recollects information. To elaborate on this point, let us take an example. Suppose you are writing an exam and you encountered a question which is similar to one you have encountered during learning. So, even though the values of the questions are changed, you still know the way to proceed to answer, right? So, how does our brain do this? The brain simply compares the question with the all sets of questions you have seen before and find the one which is closest to this question. That is how the brain recollects the or remembers the question, right? Now, this is what is implemented in memory based learning. In memory based learning, we feed the system or make the system memorize or store in the system a lot of input output pairs. For example, let x bar be a input vector. Input vector. This input vector may contain a lot of inputs. x1, x2, etc. up to xn. Okay. And the corresponding desired output to the input vector x bar is also fed into a system. Okay. Now this d can also be a vector like d1, d2, d3, etc. to dn. But for the sake of simplicity, let's take that d is a scalar quantity. So for the corresponding x bar I, we get the output as di. And by output I mean desired output. Okay. Now we feed the system with a lot of such input output pairs. Okay. And by lot I meant large chunks of data. Now suppose the system encounters a test output xt bar and the system hasn't seen this input before. So what it does is it will compare this xt bar with all the set of inputs it has already been fed with and find the closest one to xt bar. Suppose xj bar is the closest one to xt bar. Then the desired output dj corresponding to xj bar will be taken as the output of xt bar. To elaborate on this, let xj bar belongs to the set of inputs, that is x bar 1, x bar 2, etc. to x bar capital N. Now, how did we determine that xj bar is closest to the test input xt bar? By taking the Euclidean distance between xt bar and all the set of inputs, that is x1 bar, x2 bar, etc. up to xn bar. Now, for xj bar to be the closest, the Euclidean distance between xt bar and xj bar should be the minimum of Euclidean distances between xt bar and xi bar. Okay. Now this is the most important criterion of memory based learning. So keep this in mind. Okay. Now to clarify this, let's take an example. Consider a neural network to classify the inputs into two classes. Let's say class A and class B. So basically a binary classification system. So what the algorithm does is that when an input pattern is provided, it will put the pattern either to class A or class B. So initially we must have fed the algorithm with a large number of inputs and the corresponding outputs. Let us map that inputs in a space. Okay. So let's take a space of inputs actually. Now suppose the output to the input at this point is A, that is the input at this particular point of space is classified into class A, and let this also be A, let this point also be classified into A, let this point also be classified into A. Now we'll have some inputs which is classified into B. So let the input at this point be classified into class B, let the input here be classified to B, let the input here be classified to B, and here also B. So now suppose that we have a test input over here. So intuitively we can say that the output of this particular input will be B, right? Why? Because we can see that the closest input to our test input is a B. So this is how memory based learning works. But here's a drawback. Suppose before that, let me delete that. Suppose there was an error while we fed the data into the neural network, and accidentally we got one of the inputs over here classified into A. Okay, but we know that this is a false output and the correct output should be B. And now consider the old situation again. We have a test input over here. Now the closest input pattern to this test input is A, right? So the algorithm will classify the test input into class A, but we know that this is wrong, right? So in order to overcome this, we will compare the test input to the nearest neighbors. Stress on that, nearest neighbors, not neighbor. So what it does is that it will take the distance of test input to all the closest neurons in the neighborhood, and we can define the size of the neighborhood beforehand. Okay, so when the algorithm processes the data, it will find that the test input is closest to more number of B's than A. Thus it will rule out the falsely fed A and classify the test input into B itself. Thus we have overcome the drawback. Okay, that's all for memory based learning, and now we will move to Hebbian learning. Hebbian learning is the one which tries to resemble the physical structure of our brain. And by physical structure, I mean how the brain tries to strengthen or weaken a neuron synapse. Okay, it has been found by experiments that if we repeat a process continuously, the part of the brain or the neurons that are responsible for coordinating that activity will fire constantly. And if the neurons fire constantly, the synaptic weights of that neuron will increase over time. This is how the brain perfects a process. This is how the brain perfects a process. And the opposite is also true. That is, if we uh, if we do not practice some activity for a long period of time, then the synaptic strength will weaken. That is, the neurons won't be firing, so the synaptic strength will weaken. Now, in Hebbian learning, we try to implement this. We'll talk about Hebbian learning in the next lecture. So stay tuned. Thank you.